Okay, so continuing our previous discussion, we talked about convergence of sequences and pointwise convergence of functions. Now I'm going to define uniform convergence of functions. So sequence Fn converges to F uniformly, where Fn and F are functions from R to R. The sequence converges uniformly on a domain D if every epsilon greater than 0, there exists an n such that the distance between Fn at the point x and f at the point x is less than epsilon for all n greater than n and for all x in our domain D. Okay? So the difference between this definition and the pointwise definition is this quantifier, okay? So essentially, my index, capital N, okay, my index, capital N, does not depend on the choice of x. This index, capital N, will work uniformly for any choice of x in my domain, okay? So previously, okay, we stated that the sequence Fn converges to F pointwise if for all x in the domain, I can find an n, and this n can definitely be a function of x, right? I specify the x first, then I have to find the n, such that, such that Fn of x minus f of x is less than epsilon for all n greater than n, okay? So notice in the pointwise case, I fix the point, and then my choice of the index, capital N, can depend on the choice of my point, whereas in the uniform case, the choice of the index n cannot depend on x, that is independent of the choice of x. So let's get a geometric picture of what this means. So if I have a sequence of functions, okay, and I have some limit function. Let's look at my limit function. I'm going to draw it in pink, okay? Then essentially, if here's my sequence of functions, here's maybe f1, f2, f3, and then what the uniform convergence statement says is that if I specify an epsilon error, that's essentially specifying a tube around my target limit function, okay? And that tube is of width epsilon, okay? And then what this definition is telling me is that I have to find an index n such that every function in this sequence past the capital N is trapped entirely within the epsilon tube, okay? This is the geometric meaning of the uniform convergence definition, okay? Now, this does not hold for the pointwise definition, because for the pointwise case, if I look at the same limit function, okay, then it may be the case that, my limit functions never get fully trapped inside of this tube, but pointwise they still converge, okay? And let's look at an example, because that seems very non-trivial. Why don't you pause the video and try to think of an example of a sequence of functions which converges pointwise but not uniformly, okay? So I'll give you one example, okay? So if I look at the sequence x to the n, okay, on the interval 0, 1, and I'm looking on the domain d is equal to the open interval, well, half open, half closed, 0, 1. I could just choose the open interval 0, 1, okay? Then what these sequence of functions looks like is it's going to be 1 at 1, and it'll look like this, okay? And so the point is that this sequence converges pointwise to 0, okay? Because if I fix an x in the domain, then any number if it's less than 1 and I raise it to a high enough power, it's going to go to 0. Okay, so r to the n goes to 0 as n goes to infinity for r less than 1 in magnitude. Okay, so it pointwise converges to 0, but it never actually falls within an epsilon 2. Okay, it will never actually fit within an epsilon 2. So we have this weird behavior, which is that it's going to mostly fit inside the epsilon 2, but then at the very end, every element of the sequence eventually will shoot back up to 1. And so I can't fit it within the epsilon 2. And so notice that this is a very interesting difference here. It's a very deep geometric difference. So please let me know your thoughts about this.